Hi everyone, welcome to CSCI100 Lecture 20. In this lecture, we'll be talking about ethics. And this lecture is very different from your previous lectures. Previous lectures, I've taught material in these videos. You've learned something new about Python or programming languages in general. This one will be a little bit different. Here, you're not going to learn any new programming concept, but you are going to take some time with me and in class and discussion to reflect on the impact of that technology can have on the world, and also reflect on yourself as a new practitioner of this technology to make sure that you're using it for good. This lecture will be on the shorter side, and I'll be giving context for some different topics that will then take more time to discuss in class. Now, before we start with ethics, I want to answer this question of why we're talking about this. And I kind of phrased it already, but the short way to say this is computing has consequences. The work that you do and the things that you build, because technology is so ubiquitous and it's all around us, mistakes that you make or design decisions that you make can have a big impact on everyone around us. And you're here at Howard, which is a fantastic engineering school. And so you all will be going out into the real world and joining companies or starting companies, or just doing work that will fundamentally have an impact on the world. I don't know what all of you will do, but for those of you who go to like a big technology company, let's say you're working at Facebook or at Google or at Microsoft, so many people use these services. Your decisions are then multiplied, or the decisions that either you make or your team makes that you have an input on are multiplied and affects the billions of users that use those products. And so really, you're quite powerful and more powerful than you might realize. I'll, as an aside, say that for this lecture, many of these slides are taken from Josh Hugg's CS195, just computer science ethics class at Berkeley. And this was a class that I took in my undergrad and thoroughly enjoyed. And I wanted to talk with you all about some of these topics for our ethics class, our ethics lecture. It's impossible to condense a whole class down into a single lecture, but these will be some scenarios that we can think about as we talk about them in class. So to start with a very concrete thing, I'm going to talk a little bit about Therac. And I'm going to gloss over the details here, even though I have them written out in the slides. I don't want to get bogged down in them. What was Therac? Therac was a radiation therapy machine. And why do we need radiation therapy? Cancer is treated in many ways, but one of the ways that we found to treat it, other than cutting it out or using specific chemicals, is with radiation, in particular with targeted radiation. And so you take some radiation emitter and you point it in the direction of some cancerous cells, and you do some adjustments. And when you turn it on, it gives a very high radiation dose. That's very similar to what X-ray machines do, but X-ray machines only have a very low dose of radiation. With a high enough dose of radiation, and repeating that radiation multiple times, and often for a number of weeks or longer, we're able to actually kill the cells that this radiation is aiming at. And so the very first Therac machine, there was Therac-6, there was Therac-20. Therac-25 was special because this was the first computer-controlled treatment machine, where instead of manually kind of configuring something with dials, you would give a command to a computer, which would adjust all of the settings and move an arm in place and do all of the actual movement that's needed to have the right dose of radiation provided. Now, this machine saved many, many lives, like any cancer treatment machine, or any types of cancer treatment that we have. But a particular bug in this machine led to 6 accidents, 4 of which resulted in deaths. We're going to talk a little bit about those today, but for context, normally these radiation machines produce 80 to 180 rads, which are units of radiation, to a particular target area that we aim at. And 500 rads all at once to the whole body is typically fatal. And so many doses of 80 to 180 pointed at a particular place in your body can actually kill the cells there, which is what we want to kill cancer cells. This machine looked something like this. You would lay down, a patient would lay down here, and this machine would then emit radiation at whatever needs to be radiated. Now, the software running on this machine is something that you, as computer scientists now, could potentially be asked to build. Now, a few things. Of course, as you go on and learn more, you'll know what these are. But for now, you from these details, some of the design decisions that the engineers made left the software very prone to errors, especially errors related to concurrent processes, meaning that concurrent processes here communicate through shared memory. The frames that we've been talking about in the class, well, when you write something to memory on that page, imagine if you were using that page to take notes and your friend was also using that same page, that same frame in memory to take notes. This could be really dangerous because what if your friend writes over something that you wrote? And so let's say you're doing a math problem and you write down, you're halfway down through the problem and then you step away and your friend uses that same page in the notebook. Well, that's really not good because what if your friend overwrites some of your numbers? And then when you go back to continue solving your problem, you're actually solving a different problem now. So there were like fundamental design decisions that led to this, like bugs in the code. Furthermore, the user interface that the nurse operating the machine would use did not actually reflect reality. And so sometimes you would tell the machine to make changes, but those changes wouldn't actually be made, even though the user interface would say that they were made. Some of the default values when you turn on the machine produced bad behavior, and the machine didn't communicate very clearly what was wrong. It would stop if it noticed something was wrong, but it didn't communicate very clearly. And so a frustrated nurse would just start the machine again. There's some more details here on, there was this particular arm that for low current radiation needed to be out, for high current it needed to be in to attenuate the strength. And this machine had a bug where it would dole out huge amounts of radiation, like 10 times more radiation than it should, beyond a fatal amount of radiation at a particular, when it was aimed at a particular small area, not the whole body, some particular small area. And 6 times, there was this accident, 6 known times, where the machine was configured to do regular, correct treatment. A patient would come in and lay down and for treatment, and the nurse would set it up to treat the patient correctly, but the machine would actually emit much more radiation. And these 6 times, 4 of them led to deaths. So 4 people died as a result. What went wrong? So the software engineers working on this didn't provide proper documentation. And we've been talking about documentation in this class and how important it is. And so far, great. Your instructor tells you, please write out docstring or something. When you're building software that is going to be used to treat humans, you have to be very clear about its behavior and write it down so that other people can understand it. Whenever you're writing code with concurrency, and you don't know about concurrency yet, but it is just this idea of, hey, what if I share my frames or my memory or my page in a notebook with someone else? It's very important that you have an agreed upon way to do that. And these engineers didn't follow an agreed upon way to do that. The user interface wasn't great. Testing is super important. And so all these, it might have been frustrating for you why I'm asking for so many tests on these projects and on the exam. It's crucial to be able to write tests on the software that you produce because when it affects other people's lives, we need to be sure that it works correctly. Maybe one of the largest things here is when you're building software, if this software is critical, like medical software, or like a Mars rover, for example. So, for example, or the International Space Station, it's really important that you have some sort of auditing that happens. And what auditing is where you have someone else come in and look at what's being done, like a non-biased third party, to see what's actually being done. And finally here, with software or hardware or technology in general that is so important, it's important that we be able to handle errors gracefully. And in your code, we talked about raising exceptions. Yeah, what do you do if a user gives you some input that isn't something that you expected? You don't want your machine to error out and then produce deadly amounts of radiation. You need to be able to handle all of those cases. So here in class, we'll talk about this discussion question. When a software failure causes injury or death, who's responsible, or how do we think about responsibility? And especially now in this new world, how do we think about responsibility for the decision of an algorithm, especially like an AI algorithm? And even once we do that, like, what punishment do you give to whoever you decide to is responsible? And who's even deciding? Who's looking? But this Therac-25 example is a very clear case where the software that you're building, like, you all will be qualified to work on software like that, and some of you will be hired to work on medical software. And so it's very crucial that you ensure that what you're building is following proper standards and has good documentation and has fantastic testing when it can affect other people's lives. We'll revisit this discussion question in class and just talk about it all together.